In this video, I'll be completing the second part of the video on logarithmic functions. So it says here, graph f of x equals 2 to the x power and its inverse on the grid. So first of all, I'm going to go ahead and change to the y notation, and I'm going to make an xy table. And we learned when we graphed exponential functions that we would choose x to be three different values, -1, 0, and 1. And let's see, I'm going to go ahead and plug in the 0. 2 to the 0 power would be 1. 2 to the first power would be 2. And 2 to the -1, that would be a half. Now I would just remind you that these two numbers are always going to be reciprocals. In fact, when we get to the ones where we're graphing logarithmic functions, it's going to be the same way. So I'll usually plug in the 1 and get 2, and then I would just use the reciprocal. You don't really have to do any work there. So now if we're going to find the inverse, at least for now, since we're doing a graph, let's just flip our x and y values. Oh, by the way, let me graph that real quick first. Don't forget you would have an asymptote there. So that's the graph of y equals 2 to the x power. So, and we did that in the previous section. Now let's go ahead and flip the x's and y's here for the inverse. And let me go ahead and graph those. Now remember, when we graph an inverse, graphically, we can see, we talked about how the inverse will be a reflection through the line y equals x. So it's kind of helpful to put that in here. So that's the line y equals x. And we know we're going to have symmetry with respect to that line. So on this lower end here, this graph's going to look something like that. Notice for the exponential function, you have a asymptote at y equals 0. This one's going to have one at x equals 0. And then let's go ahead and finish the graph off to the right. Now, one thing I want to mention here is when you draw this, you want to make sure this looks like it's rising, because it will be. And that's important when you start looking at the range. So with the logarithmic function, this right side will be rising, sometimes quite slowly. But that is important that you try to draw your graph so it looks like it's rising. All right, so let's see. It says, what is the domain and range of f? Well, for any exponential function, we know the domain is all real numbers. And you can see that from the graph here. It goes forever left and forever right. Doesn't skip anything. The range is going to be from 0 to infinity. Notice there is no lowest y value, or I should say we don't quite get to 0, but that would be where our range starts, and then it goes up forever, so that'd be 0 to infinity. What is the domain and range of the inverse? Well, remember what we discussed when we talked about inverses. The domain and range are just going to be flipped here. So domain will be 0 to infinity, and the range will be all real numbers. And you can double check that if you look on the graph. You can see that it's true. All right, finally, we've graphed the inverse of f of x equals 2 to the x, but we actually haven't found an equation for it. So we're going to use the 4 steps that we learned previously to find the inverse. So I'm just going to remind you what those are, and we'll do the steps as we go. So first of all, we replace the function notation f of x with y. And then this is the key step. We switch x and y just like we did with the points up above. So we switch our x and our y. And then the other key step is we solve for y. Now, notice, and in fact, anytime you have a variable in the exponent, you're going to have to use logarithms in order to solve this. This is where we rewrite this in logarithmic form. This is an exponential equation The 2 is your base, the y is your exponent, and the x is the answer. And so go ahead and switch forms, write it as a log. So you should have log base 2 of x equals y. And notice by doing that, we've actually solved for y. And then finally, our last, excuse me, my last step is to switch to the inverse notation. And I forgot to write that down. Whoops. Let me change colors here. So 4 is replace y with f inverse of x. Now I'm actually going to erase that because I used that space down below. So let me go ahead and do that. But that is the 4th step, and that's what I just did on the left there. So we did find the inverse. It's log base 2 of x. So I want to make a comment here. The inverse of f of x equals b to the x, or any basic exponential function, the inverse of that is going to be log base b of x. So exponential functions and logarithmic functions are inverses of one another. These are really simple, at least in the most basic form. If I have f of x equals 5 to the x, then the inverse would be log base 5 of x. So basically I could change the base to be anything, and finding the inverse is quite simple. It looks pretty much the same, it's just a log. Just has the same base. All right, so let's go ahead and move to the next page. So this is a summary of graphing exponential and logarithmic functions. We've already looked at graphing exponential functions. Remember when we did exponential function graphs, we would choose x to be -1, 0, and 1. That's all that's saying here. And again, I want to remind you our base is greater than 0. It can't be 1. Our domain and range for the most basic form is going to be all real numbers for the domain, 0 to infinity for the range. Y equals 0 is going to be a horizontal asymptote. Now, if the base is greater than 1, I would give you the example y equals 2 to the x. So the graph of that would look something like this. If our base is greater than 1, and 2 is, then we're going to have a case where the graph is basically, I call it's an exponential growth function. And notice we're going through 0, 1. It's an increasing function. It looks like that. Now, if our base was between 0 and 1, I would think of the graph of y equals 1/2 to the x power, which looks very similar, but notice now it's increasing, or I'm sorry, decreasing. It's a decreasing function. And this is what the kind of graph that we use to model exponential decay. Now, on the other hand, for graphing log functions, notice our base is still greater, and it's greater than, and it's not equal to 1. This time, when we're doing exponential graphs, well, first of all, well, you'll see shortly, you end up choosing your y to be -1, 0, and 1. Again, that's because the logarithmic function is the inverse of the exponential function. Notice our domain and range are flipped from what they were over here. Instead of having a horizontal asymptote, we actually have a vertical asymptote at x equals 0. And I'm just going to look at this case here. When our base is greater than 1, I would think of the example y equals a log base 2 of x. Now remember, with our exponential functions, the key point that they went through was 0, 1. With the logarithmic functions, the key point is going to be 1, 0. And notice our asymptote at x equals 0. And this function basically looks a lot like the ET function, or y equals square root of x, although it's different in that it doesn't start at 0 here. In fact, whoops, let me erase that. in fact, it goes down and it approaches this asymptote here. All right, so when you're graphing exponential functions, particularly the basic form, you're going through 0, 1. When you're graphing logarithmic functions, your basic graph, you're going to be going through 1, 0. These three graphs are graphs that you should get to know. You might want to write them on a card and make sure you know what those basic graphs look like. All right, let's move on to the next slide. So it says graph each of the following logarithmic functions. So on example 1, the first thing I'm going to do is change to the y notation. And in fact, you can choose, you could make an xy chart and choose values for x, but that can be a challenge to do. You've got to really know your logarithmic functions to do that. I would encourage you to switch forms. Remember, you can do the around the world thing, 3 to the y power equals x. And so it's much easier to pick points in this form. And again, instead of choosing our x's to be -1, 0, and 1, we're going to be choosing our y's to be -1, 0, and 1. And notice that's going to be pretty easy to do. 3 to the 0 power is 1. If I replace y with 1, 3 to the 1 power, that'll be 3. And if I plug in -1, 3 to the -1 power, well, that's 1/3. But again, I would remind you, these are always going to be reciprocals, so really you don't have to really do any extra work to get that one. So let's go ahead and graph these points. And notice our asymptote's going to go there, and this is exactly what we're expecting. Our base is greater than 1, it's 3. We're going to go through 1, 0. We're going to have that ET type of graph, except for it has an asymptote at x equals 0, and the graph will look like that. Again, don't forget to draw this part so that it looks like it's rising. All right, so our domain, we're going to go from 0 to infinity. Our range, it goes down forever and it rises forever, and so it is going to be all real numbers. And that's typical for a basic logarithmic function where we're not doing any shifts or anything like that. All right, so I would encourage you to try number 2. In fact, I would, actually I'll get you started on that one. So the parent function is the log base 3 of x, which is the graph we just drew. So I would start like that. So basically you just have to figure out how to transform this graph to the new one. All right, so the x minus 2, the minus 2 is with the x in parentheses here. It's going to cause a horizontal shift right 2. And so we're going to move each of our points right 2. Now notice this asymptote, if we move our graph right 2, the asymptote's going to need to move right 2. In fact, you can kind of see what's going on over here. So let's put in an asymptote right 2 there. So that would be x equals 2. And your graph looks like that. So our domain, notice that's going to change. Our leftmost point, we don't quite get to 2. So it'll be 2, and then it goes forever right. So 2 to infinity. Notice this graph does go down forever. There is no highest point, so no lowest or highest point. The range is all real numbers. And you're going to find with the logarithmic graphs that your range is going to be all real numbers even after you do a shift, or shifts or reflections. All right, let's move on to the next page. So on number 3 here, it says graph f of x equals -2 plus the log of x, or the common log of x. Now, our parent function is going to be the log of x. I'm going to go ahead and write the 10, although we don't normally write the 10 as our base. This is a common log, which has a base of 10. And I'm going to switch forms. It'll be 10 to the y power equals x. So remember, this is the way I like to do the logarithmic graphs. We're graphing the parent function. we're going to choose y to be negative 1, 0, and 1. And again, it's much easier to work with this form than this form here. Or at least for most students, it seems to be easier. All right, so if I plug in 0 for y, x will equal 10 to the 0, which is 1. If I plug in 1 for y, x will equal 10 to the first power, which is 10. And of course, our answer here will be 1/10 because it's 10 to the negative 1 power. So let's go ahead and graph the parent function. Now this one's a little bit tricky to draw. What did I do? Oh, hold on just a second. We'll stop right there. So it's a little bit tricky to draw this part here, but actually we're not going to draw that until we do our shift. So now I just want to point out that this function could be written this way, the common log of x minus 2. The key is the minus 2 is not with the x, it's separate. It's separate from the function part. And so this is going to cause a vertical shift. In fact, a lot of times books will put the minus 2 first. But this is going to be a vertical shift down 2. And so let's go ahead and move our points down 2. Now notice the asymptote, when you move it down 2, that's not going to change the asymptote. And so that won't change. So let's go ahead and draw the graph. Again, this is a little tricky, but not too bad. All right, so our domain is going to be 0 to infinity, not counting 0. And our range will be all real numbers. All right, let's look at number 4. Now you can try number 4, but you would have to, your parent is going to be y equals the natural log of x. And I'm going to go ahead and write that using the e. Remember, ln means log base e. And so then I would encourage you to switch forms. And actually, I'll go a little farther here. And make a table where y is negative 1, 0, and 1. And so I would encourage you to see if you can finish this whole problem, and then I would have you watch the video. All right, so if you plug in 0 for y, x equals e to the 0, which is 1. If you plug in 1, e to the 1 power is e, and we said that's about 2.7. It's 2.718, and 2.7 is good enough here. And then if we plug in negative 1 for y, e to the negative 1, well, you'll need to put that into your calculator, and you get about 0.4, just to 1 decimal place. All right, so let's go ahead and put our parent function in. The asymptote would be right there. Now remember, the natural log of x, the graph is really not much different than the log base 2 of x. Actually, I should in fact, it's not much different than the graph of log base 3 of x, which we just did. And we did log base 2 of x a couple problems before. And that's because our base is 2.7. It's between 2 and 3. Anyway, let's go ahead and look at what transformations we have here. Notice the minus is out in front of the function. We know that causes a reflection through the x-axis. This is our most common type of reflection. And then we know the plus 3, since it's inside with the x, it's going to cause a horizontal shift. It's not like number 3 where we had a vertical shift. So this is the one that works kind of opposite, and so that would be left 3. Now normally we do reflections first. I noticed that this book sometimes does it in a little bit different order, but let's go ahead and reflect first. And so you get this graph here. This is actually the graph y equals minus ln x. All we did was reflect our original 3 points through this line here. All right, and then we're going to move everything left 3. Notice the asymptote's also going to move left 3. And so we're going to get a graph that looks like that. So our domain is our leftmost point. We don't quite get to -3. And then it goes right forever. For the range, going from the lowest to the highest point, again, this is going to be all real numbers. All right, we've got one more thing to cover. That's the change of base formula. Now, this is the change of base formula, and notice we start with some base b, and we end up with a base of 10. Remember, if we don't write the base, it's understood to be a common log, which is base 10. Now, I'm doing this with common logs. You could also, you could have said this equals the natural log of m over the natural log of b. We can use common logs or natural logs. I'm just going to use the common logs. All right, so let's see if we can follow the steps here. So we start with letting x equal log base b of m. So how did I get this? Well, isn't that just a matter of switching forms? Change to exponential form. And then here, all I did was take the log of each side, base 10, and then actually going from here to here, they use something that we will talk about in the next section. We're actually able to move this exponent out front. So you'll see that when we get to the next section. And then finally, I just divided both sides by the log of b, and we get x solved. And so, but remember, we said that x was log base b of m, and so that's how we get our final answer here, which is what we were trying to prove. All right, so let's go ahead and use this now. It says evaluate to 3 places log base 3 of 8. So by the change of base formula, this is the log of 8 over the log of 3. Now when you put these into your calculator, you want to be careful. I would recommend that you put parentheses around the numbers here. So put that into your calculator. You should get 1.828 or 1.8928. Now it says 3 decimals here, but I did 4. I usually do 4. I think this book was using 3. But either way, we like to have at least 3 or 4 decimal places, because when we check our answer, we want to see that it's close enough that we believe that we have the right answer. Now I want to remind you, log base 3 of 8 is an exponent. It's the exponent you put on a base of 3 to get 8. Well, we can easily check our answer here. 3 to this power should equal 8. And if you plug that into your calculator, you'll see that it's true. Highly encourage you to check yourself on these. When we get to the part or the section where we're solving equations, that's going to be very helpful. All right, last one. Number 2, I would encourage you to go ahead and do this one. So you should have written the log base 5, or the log of 5 over the log of 2. When you put that into your calculator, you get 2.3219. So again, we can check ourselves. 2 to that power should equal 5. And if you plug that in, you will find that that's true. Now, it won't say exactly 5. It might say 5.00 something, or it might be 4.999. But you'll see that, again, we're estimating our answer, and so that's why it doesn't show as exactly being 5. All right, I want to mention one last thing here. At the beginning of this lesson, on the first page, we got to this problem and we couldn't solve for x. We didn't have a way to isolate x or get it by itself. Well, when we learned about logarithms, we learned that we could switch forms. In fact, anytime you have an exponent in the variable, by changing to a log, you can solve for that variable. And then once we did that, notice what we had here. Well, we had done this and we solved for x, but we didn't actually know what it equals. Well, notice we finally have gotten an answer there. And so our answer is just 2.3219. All right, and so that's going to be it for this lesson.